of Professor Urbasi. Professor Urbasi Sinha is working at Raman Research Institute, Bangalore. She is heading the Quantum Information and Computing Laboratory at RRI, Bangalore. She is also an associate faculty member at Institute of Quantum Computing, University of Waterloo, Canada, and University of Toronto, Canada. Professor Urbasi completed her MSc degree in physics and also the PhD from University of Cambridge, UK. She was a postdoctoral research associate at Cavendish Lab, UK. She has won numerous awards and has also published a number of papers and is a well-known person in the field of quantum technology. More specifically, I will say quantum communication. So, actually, without any further delay, let us invite Professor Urbasi to speak about her work in this latest area of research, as well as wider applications of quantum technology. So, Professor Urbasi, please.
Yes, thank you, Dr. Bhatnagar. Can you hear me and see me?
Yes.
Okay, yeah. So I'll just share my screen first, just to ensure that it still works. Yeah, it is fine, right? You can see my screen? Hello? Hello?
Yes, we can see your screen.
Yeah, okay, yes. So, thank you, Dr. Bhatnagar, for the kind introduction. And of course, thanks to the organizers and the IEEE Photonics Society Bombay chapter for this invitation to speak to you today. I was told by Dr. Bhatnagar that the audience primarily consists of students from the Bombay area. So I have kept my talk at a level that, I can actually communicate with a wide background of students to basically give you a sense and about this field of quantum communications, and also a little bit about the kind of work we have been doing at RRI Bangalore on this domain. Okay. So this is a quote that I actually am very fond of. So today's science is tomorrow's technology. And you can see from the person who has been quoted as making this statement, it is obvious what technology we are talking about in this particular quote. But having said that, this is something which actually very nicely applies to quantum science and technology. So the kind of stuff that we do now in basic sciences and fundamental science in the domain of quantum forms the basis for the technological applications, which are also very interesting from the quantum arena. So for instance, decades ago when the laser was discovered, I don't think the people who discovered it were really aware of the kind of usage that it has been subjected to over the last several decades. So it is very difficult to actually predict what kind of technology breakthrough would happen based on today's science. But then quantum is an area where this is always going hand in hand. So there are things which are done at the fundamental science level, and then those are again picked up for their technological ramifications by our colleagues who are working more in the domain of applications. So this is sort of a framework where quantum communications is also a very interesting example. Okay. As we know, while we talk about quantum science, it has, of course, taken up a lot of discussion space over the last couple of years, I would say, with our government announcing a national mission on quantum technology and its applications. And that is, supposed to be dealing with different areas of quantum science and technology, both fundamental as well as application oriented. And there are four main themes there. One is quantum computing, one is quantum sensing, then we have quantum materials, and of course we have quantum communications, which is what today's talk is going to focus on. Okay. I belong to the light and matter physics group, and we have other faculty members in this group who are working on different areas of, light and matter physics, some of them with quantum interests. And of course, I head the quantum information computing and communications research at RRI. So before I go on to, the main part of the discussion, which would be on quantum communications, I wanted to give the students specifically, a brief overview of the various types of activities that we are involved in at Quick Lab at RRI. And of course, quantum communications is one of them, but it is not the only one. Okay. This is what governs a lot of what we do, the big picture really, which may seem a little bit bleak if you just read it as it stands, that, our theoretical understanding of the universe is very incomplete. We don't really understand more than 80% of what the universe is made of. Okay. And so, in fact, this is very true. And so that is why there is a lot of research going into understanding these aspects of the universe. So then it comes a question, right? So how well do we understand the laws which govern the various aspects that we are dealing with in daily life? For my purpose, it would be the laws of physics and the laws of quantum mechanics. So now this understanding of the laws is very important because a little bit of change in our understanding will have deep-seated ramifications in various aspects, even to do with the context of the early universe. So fundamental tests are very important, and that is one of the areas where our lab is very much invested in. Fundamental tests of various principles of quantum mechanics and quantum optics. Okay, and then of course come the two-pronged applications which we are investigating. One is quantum computation, and of course I won't go into the details of that here, but as the students must already know, it's a very important research direction. And of course, quantum computers are projected to be able to solve certain problems for which there is no efficient classical algorithm. But then more importantly, solutions for even what is possible in classical computing would be exponentially faster for certain problems. Okay, and these are very important and interesting problems, and quantum computing is a very, thriving area of research in quantum technologies. The area which we will talk about today is, of course, quantum cryptography, which forms a part of quantum communications. And this is, of course, very important from the practical point of view. And as I would go on to tell you that this is indeed the most highly advanced quantum technology application from the principles of quantum mechanics. And it is guaranteeing perfectly secure communication. And this is, of course, the need of the hour. Here I am speaking to a diverse group on a Saturday evening without even, walking an inch out of my house. And this is one of the ramifications of everything going very much digital over the last couple of years. While the rest of it is not very pleasant, the reason why this has happened, this is a ramification. At the moment, I would say it is a positive side of, us being forced to come up with new ways in which we can still continue existing and communicating and making progress in science. And so this is something which now is possible, giving a talk to students in Bombay while sitting right at my house in Bengaluru. And so, however, this is not an example of secure communication. This is something, no secrets here, but then there are examples where this would be very important, and we will come to that. So as I mentioned, our lab deals with experimental as well as theoretical problems relating to fundamental tests of quantum mechanics, quantum computation, and quantum communication. Okay, and this is, a snapshot of various activities in the lab. Let me just get the pointer here. Yeah, so various activities, and, of course, it's not a time for visits yet, but then hopefully soon. The basic technology on the basis of which we explore our science is on, photons, single photons. So we work on photonic quantum science and technologies, and of course, I'm speaking to the photonics chapter. And so if you wanted to have, for the students who are not familiar with this, and I'm sure this is not a very common topic, there are different ways in which, these photons can be realized. Okay, and it is very interesting because if you think about it, I'm sitting in a room which has sufficient light so that my video works for you, and so I'm surrounded by photons, right? So in fact, you would say, why do I need to do anything special to actually work with them? Because of course this is all around us. We are always surrounded by light of different types, right? But that is not, of course, going to help us in our applications, in our science, because when we deal with quantum oriented research, we deal with a single particle of light, or maybe two particles which share a very strong correlation, which is called quantum entanglement. So this is something which cannot just be produced by, let's say, simply dimming down the light in my room. This requires special, means and specialized technology. And so there are different ways of realizing them. And this is a nice, I would say, overview, which is written at a slightly popular level, so that, you can get a big picture without going into the detailed math. And in fact, very soon there will be an encyclopedia of materials which will be published by Elsevier, where I have written a book, where I've written a chapter on this topic, which is a little more advanced even. So once that becomes available, you can have a look at that as well, because that is more detailed than this one. Okay, and so different ways of doing it, and what we are doing in our lab is working on what is called spontaneous parametric down conversion, which is a way of creating these photons using what is called nonlinear optics. Okay, but here I won't get into the details of those because that is a talk by itself, but it suffices to say that we produce photons which come as pairs. Okay, a pair of photons produced at a time, and so and these pairs, they actually they traverse cones when we solve the equation, and I leave it at that. So if you go with the cones, then you can see that this red portion here, it's a part of a cone, okay, and this red portion is a part of a different cone. So these two photons, one of them is on this cone, the other is on this cone, and they are always perfectly matched in terms of energy and momentum and so on. And so if one of the photons is here, the other is here, and if you think about it, this particular yellow point that you can see, this is the intersection of these two cones, right? Now this guy, it could belong to either the right cone or the left cone. So you don't know which one it belongs to. And this is what defines my entangled state. Okay. So entanglement is a correlation in which, you cannot define them separately, the particle states. But if you know of one, then you know of what is happening with the other. And so this is my entangled state. And so I have to do a lot of optical alignment in order to harness this entanglement. And so this is a picture from the lab of an entangled photon source cone geometry. Okay. Going on to the applications other than quantum communications. So as I mentioned, one of our key areas is fundamental tests of quantum mechanics. And so you can see here, yes, that this is a series of work that we have done in which we have tested the superposition principle itself. And of course, for people who have been privy to at least some course in physics, you would know that superposition is one of the important tenets, most important tenets of quantum physics, which in fact is the basis for quantum computing. So here we have challenged the use of the superposition principle, the common use in interference experiments, and we have shown that it is incomplete, it requires a correction, and this is our first measurement of the correction term as we speak. Okay, and so this is on superposition and Born rule. These are two fundamental tenets of quantum physics. This is an experiment in which we did a fundamental quantum optics experiment. And again, without going into the details, what happens is when you have photons, you need to have different ways of diagnosing whether you really are dealing with single photons. Because of course you can't see them, right? Because you're dealing with a single particle of light. So there are different ways in which you can figure out whether you actually have a single photon. And one of them is having two photons incident on two input ports of what is called a beam splitter. Okay. And so then if these two photons are perfectly indistinguishable, then these photons, they always exit from the beam splitter either one way or the other, like they both go together, either one way or the other. They don't split into 1-1. So they form the 2-0 minus 0-2 state, we call it. And so what that means is that at 0 time delay, the cross correlation between these two detections is going to be a 0. And this is called the famous Hong-O-Mandel dip. Okay. And so this is one of the diagnostics of photon sources. So what we did in this experiment is challenge this diagnostic actually. And we saw that this is a dip which we can actually measure by even using classical pulses with complete phase control. So we challenged the use of the Hong-O-Mandel as a diagnostic for photon sources and produced and proposed a new one, which is called the complementarity test. Again, I won't get into the details, but again, this is dealing with a fundamental quantum optics phenomena, which is the basis for quantum teleportation, for instance, which is a quantum communications protocol. Yes. One example of an application that we have worked on, which again is very much ingrained in fundamental science, is a new state estimation protocol that we have come up with, which is called quantum state interferography. Now, again, no details here, but what happens is that, now I think the younger people will understand this very well. So I'm telling you that, okay, there are all these beautiful applications, whether it's computing, whether it's communications, and everything begins with a quantum state, right? So you have a quantum state, you perform a series of operations on it. They could be gate operations, some protocol, and then you end up with a result, right? But then a measurement. But then these operations are performed by assuming that you have a certain knowledge about the initial quantum state. But then a very interesting aspect of quantum mechanics is that if you have a quantum system and if you measure it, then you destroy it. Okay, you basically change it to something else. So now comes the point. How do I know what is the state that I'm dealing with? Because if I measure it, then I actually lose it. So what people have traditionally done, the community, is that they have done a method called quantum state tomography. Okay, and this is something again which you guys will understand, because this is very similar to the CT scan. Okay, and very much in the news these days during COVID second wave, in fact, right? And so what is the basis for the CT scan? It's a tomography. The T is tomography. So what is happening is that so let's say it is the CT scan of the lungs or something like that. So instead of invasively doing some measurement, this organ, we actually image it with different projections. Okay, so different projections of this organ, they are imaged, and then these images are stitched together, which is called tomography. And that gives us a reconstruction of the image. Okay, that is how the organ looks. We don't measure it directly, but it's a reconstruction technique. So similarly for the quantum state, we do projective measurements in different bases and then reconstruct the quantum state. That is called quantum state tomography. But the problem is that when you go to higher and higher dimensions for the system, quantum state tomography scales very badly. It scales as d square. So for a 3-dimensional system, you require 9 sets of measurements and so on. So it's a very bad scaling factor. So people have been working on trying to have a more efficient scaling for quantum state estimation. And in our technique called quantum state interferography, we have been able to bring the scaling factor down to d-1, which means that for a qubit system, you need only 1 set of measurements. So instead of d square, it is now d-1. So it's a very good scaling advantage and a completely new way of doing this quantum state estimation. And as you can understand, this has ramifications, very important ramifications in quantum communications, for instance, because if I have a very good knowledge of the initial state, only then the resulting protocol will be secure. So the security of the protocol will very much depend on whether I'm well aware of what I'm dealing with, right, as the quantum state. So, and also, this method has very good, probability, and we have discussed this very much in detail in the paper, which you can have a look at, of miniaturization. Okay, so we can envisage, and we have shown how, you can have a little pocket size, quantum state interferometer, which you can kind of carry around. And then if you want to know what is the quantum state, then essentially you have a single shot measurement, which will give you the answer. Okay, so this possibility exists with this technique, as I mentioned, and so this is how it looks, in the interferometer schematic, and this is important that we can determine an unknown qubit state using a single shot measurement. We can also quantify the entanglement and so on, but this is the important point, that it gives a fantastic scaling advantage over conventional quantum state tomography, and where we are using as a resource the fundamental principle of interference. And as you guys might know, interference is supposed to be something which has been, at the heart of quantum mechanics. So Richard Feynman very famously said that interference contains within it all the mysteries of quantum. And in fact, the Young's double slit experiment was voted as the most beautiful experiment of all time by readers of the physics world around 10 years ago. So a lot of very important fundamental aspects to this phenomena, which again has this very interesting ramification as a state estimation technique, okay? Important in quantum communications, among other things. Then we are also working on quantum computing and quantum communication in higher dimensions, which I won't get into the details, but if students want to have a look at this article that I was invited to write for the Scientific American, which again is written in a popular level holistic sense to give you a feel for our research in higher dimensional systems. Okay, we are doing lots of stuff on quantum measurements, as well as on studies of different aspects of quantum entanglement, which of course is a key resource in quantum communications and other applications of quantum. Now I go on to quantum communication, which is what I would spend more time discussing here. And in fact, in quantum communication, the main quantum aspect is the key distribution problem. Okay, so as we will see, there are different aspects of quantum communication which are very much similar to the classical way of doing things, but it is the key distribution where the quantum element becomes important and is used and makes this very different from the classical key distribution that we are used to. And I would say this is the most quote unquote practical quantum technology because it is at a much higher technology readiness level than, let's say, the other areas of quantum technology. However, having said that, that doesn't mean that there is nothing left to do here. There are many, many interesting areas left to explore, both from the science and technology point of view, new protocols, new securities, and in fact, what I'll give you, describe to you an experiment which we have done where we have actually been able to increase the security of the protocol. So many things to do, increase the distance of communication and so on and so forth. The field is very active and there's a lot of work to be done by scientists and engineers alike. Okay. Why, however, you should worry? Well, you should worry if you are involved in any of these 4 applications that I have listed out, whether it's purchasing something using a credit card, whether it's banking, online banking, voting. Hopefully, most of the students I'm speaking to are in the voting age, right? And so voting for your government. And then, of course, defense strategic communication, which only some people are directly involved in, which is our defense sector. But then all of these things that you see here listed and many others, they fall under what I would call strategic communication domain, right? In all these applications, it's very important that the communication is between the intended parties. If I'm buying something online and if I give my bank details to the vendor, it should not be intercepted by an eavesdropper, right? Because of course, then my information becomes vulnerable. And so this is something which is called a strategic communication. And all of us are involved in it in different ways, some more so than others, but all of us do something or the other which involves strategic communication. And all of this is at a risk of being compromised with quantum computers. Okay, so information communicated through classical cryptography now, this will be compromised with quantum computers. We need to take steps now so that we can prevent this catastrophe. And the solution is quantum cryptography. Let me explain a little bit more. So what is wrong with classical cryptography? It's not particularly wrong, but it is just that unconditional security is not possible. So for instance, most of classical cryptography right now is based on what is called the RSA protocol. Okay, and the RSA protocol is based on the mathematical complexity of factoring large numbers. What does that mean? That means that, if I tell you what is 3 times 7, you can jump and say 21 very easily. But if I tell you what are the prime factors of 3, 4, 5, 6, 7, 1, it is not so straightforward. So factorization is a hard problem. Okay, and the RSA protocol is based on this hardness being true. Now, this is Peter Shor, who came up with what is called the Shor's algorithm, which is an algorithm using quantum gates that can perform factorization in polynomial time, which means that the hardness class of factorization can be changed by using Shor's algorithm to becoming much easier. So which, of course, you understand what that means, that computational resources, they grow very fast, okay? And today's hard problem could be solved tomorrow using brute force attack. New algorithms can come for classical computers. Then, of course, there is a realization of quantum computers, which will run, for instance, Shor's algorithm. Yeah. So my security should be independent of future advancements in computational power, new algorithms or new technology. That is, it should be future secure. This is very important. So whatever we are using right now for the security, that is broken 10 years down the line, then my currently secure information shouldn't become vulnerable. For instance, if I have now created a will for who will inherit whatever little I own, and then okay, now I don't want to say 10 years down the line, but maybe few decades down the line, when somebody actually goes on to own that, that person should actually be getting the right stuff, right? And that will only happen if my security of my, the bank or wherever I have stored my life savings, that doesn't go into the wrong hands. But that can happen if indeed quantum computers become very real very, very soon, and Shor's algorithm works and RSA protocol is vulnerable. Okay, so future security is very important. So this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And the most important part, as I mentioned earlier, is the key distribution part, which is quantum key distribution. Okay, and so just to give you an example, this is the current status, the RSA cryptography protocol. So see, this 2048 RSA key length, the security claim is beyond secure till 2030. Okay, and you need security beyond 2030, then you need a longer key length. So popular quote by Krista from Microsoft Research, the RSA 2048 challenge problem would take 1 billion years with a classical computer. A quantum computer could do it in 100 seconds. Okay. So this is the current record, and things are happening as we speak. Maybe this has now been broken. But please remember that a quantum computer will employ Shor's algorithm to solve the factorization problem. And it is estimated that 2048-bit RSA keys could be broken on a quantum computer comprising 4,000 qubits and 100 million gates. So we have to know that we are not quite there yet with the quantum computing technology. We don't have as many qubits and gates as of now. But that doesn't mean we become complacent, because this is happening very, very quickly. It's not going up in a linear way by any stretch of the imagination. Quantum computing research is going at a super fast rate. And so this possibility could happen anytime. Maybe it's next year or maybe 5 years down the line, but it's not definitely going to be infinitely far in the future. No. And so once this happens, then this becomes a problem, right? So we need to take steps now so that it's not a problem anymore, because quantum computing will solve many problems which are of benefit to society, right? If it also manages to break our security, it shouldn't be allowed to do so. And so we need to take steps now and change our paradigm towards different domains so that this is not a problem anymore. And so that is why it is important to have different kinds of research in quantum communications. Okay. So how does quantum mechanics protect information? This is, of course, a talk by itself, so I won't get into the details, but we can summarize the idea by saying that these are the basic principles which are used in several ways, complicated ways to actually get this security. Measurement disturbs the signal on an average. As I mentioned, that is one of the things, you see, which indeed led to new quantum state estimation technique that I talked about. If the signals are not, but then here what this means is that if it disturbs, that means an eavesdropper won't get away with knowing things just like that. Okay. And that is where, an unknown quantum state cannot be cloned by an adversary, which is the no cloning theorem. If the signals are non-orthogonal, adversary cannot ascertain which one it is, which is the Heisenberg's uncertainty principle. And then, of course, we have quantum entanglement, which is a quantum correlation that can be used to protect information. Okay. And so this is just a nutshell. But then different offshoots of these basic fundamental principles forms the basis for quantum communication security. And there are different approaches to QKD. We have prepare and measure based approaches where the security is based on uncertainty principle. Popular ones are the BB84 protocol, the B92 protocol, and several variants of them. Then we have entanglement based QKD where the security is based on entanglement. Popular ones are BBM92 protocol, the Eckert91 protocol, and again, several variants among them. Now, just to give you a little idea of one of the popular protocols, which is the BB84 protocol. Okay, so the BB84 protocol is based on essentially what is called prepare and measure based QKD, which means that we prepare a single photon, we encode it in a certain state, and then we send it along. And so that is the bit value. And then, of course, the sender is, let's say, Alice, receiver is Bob. Bob also has to do certain sets of steps and measurements in order to establish a key between Alice and Bob. No entanglement is involved here. So what we are going to do is have a little cartoon based understanding of the BB84 protocol. So here I have a single photon source. And these are my color encodings. If I'm going to prepare it in the rectilinear basis, so as you know, the rectilinear basis is essentially, let's say, the HV basis in terms of polarization of a photon. And then this is the diagonal basis, which is the plus 45, minus 45 basis. Okay. And so we can have then 4 possible encodings: rectilinear 0, plus 45 0, rectilinear 1, minus 45 1. Okay, so this is my encodings. So rectilinear 0 is red, diagonal 0 is yellow, rectilinear 1 is blue, diagonal 1 is green. So essentially what I'm going to do is I have a single photon source. It is Alice is randomly going to select one of these bases to encode this photon in. And it's very important that this is random. Okay, this randomness forms the basis for the security. Okay, and so this randomness is very important. So random selection of basis for encoding, and then so this happens, and say it has encoded in R0. Okay, and so this is what has happened, and so this goes to Bob. Bob also does a random selection of the basis to decode this photon state. Okay, so he does that, and let's say he ends up measuring it in the diagonal basis. Okay, and if he measures in diagonal, then you can see he will measure a bit value 1. Whereas Alice actually had encoded it in the bit value 0 with rectilinear. So this can happen, right? So similarly, again, different such possibilities will happen, that Alice will randomly select between different bases to encode, and Bob will decode. Okay, and so these are the things. So now here you can see that only in some of them these basis choices match, and of course it's random. So Alice and Bob do not really know when that would happen. So what they do is, through a classical channel, they share their basis information, not the bit information, because if they share the bit, then there is no security. They only share the basis information because only they know what that means. So if they share the basis information and they see that they have the same basis choice, then they retain the bit corresponding to that basis. So they discard all these and only retain this. Okay. So just to summarize, Alice's operations: prepare single photon, different types of sources, including weak coherent pulse source, spontaneous parametric down conversion source, etc. Random selection of polarization basis for each photon between rectilinear and diagonal. Random selection of polarization between 2 orthogonal states in each basis. Then they record the time stamping and polarization state for each photon. Send stream of photons to Bob. Okay, Bob, what he does? He does a random selection of polarization basis for each photon, again between rectilinear and diagonal, measures each photon in the selected basis, and records time stamping and polarization state for the detected photons. Right? Together, Alice's and Bob's operations send time stamping and basis selection for each photon over classical channel, compare the selected basis for correlated events, consider only those events where basis choice match, and discard the rest. Okay? So critical elements to be developed in QKD, you would have to have a quantum source, and there are different possibilities, as I mentioned, and again in that review article you can see. But then, of course, it's very important that it is really a quantum source and not just a classical source, because then you will not get the security. Okay. Then there are lots of simulations which need to be done to ensure that you have the protocol sorted, because it's not just straightforward to set it up. It's of course a full-blown protocol involving a lot of optics. So that is your protocol step. And then once the QKD protocol is done, which is of course the detail that I'm not showing in this slide, we just went through it for the BB84, you will have a key established between Alice and Bob. Then comes the sifting step, where you get rid of those where the basis does not match. Then you have some classical post-processing steps which ensure that you get a secure key from this sifted key. Okay, and so as you can see, this part of the thing is the quantum area, and this part is actually classical algorithm. Okay. Why do we need entanglement then? Because of course, I just mentioned about prepare and measure based protocol. And as you can see, this choice of basis and this orthogonal basis, that the entire thing is hinging on Heisenberg's uncertainty principle. So if, Eve tries to measure in, let's say, the 45 basis, then, she will have some probability of H and some of V. So she will not be able to distinguish perfectly because Alice is choosing to send between H, 45, V and minus 45. That is where this uncertainty principle is coming in, which is what gives this protocol its security. Okay. But then having said that, here we are still dependent on, this photon source and of course the various things which define the protocol. The source itself is let's say some sort of a device, and there are many other devices involved in this. Now, what we want to do is go towards what is called device-independent quantum key distribution. So, device-independent quantum key distribution protocols aim at generating a secret key between two parties in a probably secure way without making assumptions about the internal working of the quantum devices used in the protocol. So, now, for instance, if, you're going to set up a source, suppose you buy it from some vendor, maybe some people do that. Of course, we don't do that. We set it up ourselves because we want to have complete control on its properties. But then having said that, still you have to buy certain components. So these devices could be compromised if it is coming from some vendor who's malicious. So then, this compromised device could then lend itself towards insecurity in the protocol. How much do we trust our devices? What about security vulnerability, which may be introduced at the device level itself? So we need QKD, which is device independent. Okay. So entanglement-based QKD is the only known route towards device-independent QKD, and that is why entanglement-based QKD is necessary. Okay, among other things, there are other advantages, other advantages and disadvantages. I mean, there are different pros and cons of different types of protocols, but then the bottom line is entanglement is necessary for this device independence. So longer distances are also possible through entanglement swapping-based repeaters. Okay. So going on to the experiments at our lab at RRI Bangalore. Okay, so we have of course done almost, so whatever we have discussed so far, we have demonstrated in our lab. So we have performed prepare and measure based QKD protocols using our single photon sources based on SPDC and using the uncertainty principle, that is the non-orthogonality of the states for the security. Okay, this is in 2017, we have done the first demonstration of VB84 protocol in the lab. A couple of years ago, we did a new version of the B92 experiment. So now the general idea of the B92 protocol is, in Alice's operations, Alice prepares a single photon. So now again, different types of sources, WCP, SPDC, etc. Random selection of polarization state for each photon between V and plus. So here, please note that it's only two bases, okay? So between V and plus, and these are non-orthogonal, right? In VB84, we have 4 basis choices. And so B92 deals with 2 bases. So, in some sense, there is a resource advantage in B92 because you only need 2 different encodings. So essentially 2 sources are enough, okay? So record timestamping and polarization state for each photon, send stream of photons to Bob. In Bob's case, again, random selection of polarization bases between H and minus. So the opposite of what Alice has encoded it in. Measure each photon in the selected basis, record timestamping and polarization state for detected photons, and sends timestamping data to Alice over the classical channel. So now Alice's operations compare Bob's timestamping data and consider only correlated events, discard the rest. Okay. So now if you see, this is what happens. Again, similar to my BB84, table. Again, you can have different polarization state and bit values sent. Again, in Bob's case, he can also, because it's all random, in some cases only, you will have a match. So as I mentioned here, it will be the opposite. So V plus H minus. Okay, so choice of projective measurement considered is either V or minus. Okay. So now, this is a schematic of our B92 protocol. Again, I'll skip the details here. So we just discussed this. But then you can have a look, of course, at this publication because it has a lot of detail, which I'm definitely not going to cover in today's talk. This is the Alice and Bob setup. This is the Alice part. This is the Bob part. Okay. And this is the entire, schematic, various components. This is Bob's part. So important here is, of course, the key rate and the quantum bit error rate that we measured. So as you can see, we have a key rate of around 50 kilobits per second and a quantum bit error rate which is less than 4.8%. Okay, and now this 4.8 is a very important number here. So something that you have to bear in mind is that, it is not just about setting something up and generating a key. The error is something which also needs to be in control. So every protocol comes with what is called its information theoretic security threshold, which means that there is a lot of information theory which goes in here, on the basis of which you set up threshold values beyond which the protocol is not useful, that implementation of the protocol is not useful for secure communication. So the error had better be below that threshold, and for B92 it's 4.8%. Okay, and so we did a lot of optimization techniques and theory behind this implementation of the experiment, where we restricted our quantum bit error rate to 4.8%. Okay, and to our knowledge till date, the best available B92 setup using SPDC source has reported a key rate of 31.6 kilobits per second and Q-bar of 10.5%, which is actually even above the information theoretics threshold for 0.4 meters transmission. So clearly, our demonstration is actually has a much higher key rate and much lower Q-bar for a longer transmission of 2 meters. Okay, so it's the best available in literature so far using SPDC. And also, in fact, this particular experiment is India's first published free space quantum key distribution experiment in an internationally peer-reviewed journal. Okay. So why B92? I mean, just a little bit about the novelties in our setup. First of all, we have used heralded single photon source from photons from spontaneous parametric down conversion. Most of the experimental previous works, they used weak coherent pulse. And this actually creates a security threat. Okay. An eavesdropper can implement what is called a photon number splitting attack on the protocol, because the probability of multi-photons in a weak coherent pulse source is significant. On the other hand, heralded single photon pulse generated from SPDC with low pump power typically has a very low probability of multi-photon generation compared to WCP. So our experimental setup is advantageous in terms of security. Okay. We have also used what is called true randomness in our randomness requirements. In most of the experiments, source of randomness for Alice while preparing random polarization states is a pseudo-random number generator. Okay. In our setup, we use a symmetric non-polarizing beam splitter, where the choice of which path to take can be considered truly random for the case of a single photon. Then we have done an interesting implementation where we have correlated the polarization with the temporal degree of freedom, a slight detail which I won't get into here, but this modification makes the protocol tolerant to external noise. Okay. And then we also have a very high key rate and a lower Q-bar, and as I mentioned, to the best of our knowledge, this is the highest value in a heralded single photon based B92 setup, and that has been reported in literature so far. Okay. We also, the students of course did this. They use the key to encrypt and decrypt a very popular image. And of course, this is the important part, this is the encrypted image. And of course, you are not able to make out what is the actual image. So this is a good candidate for securely sending this cat image, which is just an example, but just to give you an idea. And of course, if it did not work out, we may have sent a different image. Okay. Now going on to entanglement-based protocols, we have performed these with our dedicated entangled photon sources based on SPDC and using entanglement measures as the source of security. This is a schematic of our entangled photon source. This is, the experiment in the lab. This is the source, and these are the Alice and Bob setups. Okay, and so we have a very high concurrence value. Concurrence is the measure of entanglement. So again, how do you know you have entanglement? You have to measure it, right? So concurrence is like the kilogram of entanglement. So it's a measure. So concurrence maximum value possible is 1. And so we have achieved a very high level of concurrence, which will mean that this will have important ramifications in the security aspects of the protocol that we are demonstrating. Okay. Going on to this particular paper, which I already talked about from the experimental perspective. This, as I mentioned, is an in-lab experimental demonstration of the B92 protocol, and it's It's a variant of the original one, which gives us higher key rate as well as higher security. We also have a patent application on certain aspects of this ongoing work. And this is what I wanted to discuss a little bit. So now, and in fact, this particular work, it was very much, appreciated by the public, in the public domain, with a lot of interest shown in our experiment, as well as simulation software that we have introduced through this work, which I will tell you a little bit about. Okay. Yeah. So going on to the simulation aspect of this work, there are different simulation toolkits which exist for QKD in literature. Okay. And so some of the common ones which you will find if you search are these ones, and then there are others. Okay. But what we wanted is, quick and precise simulation of the physical processes considering realistic experimental imperfections. Okay. Simulation of the single photon source, detection module, background noise in more details, and the generalization and applicability to all existing protocols. And so none of these existing softwares actually satisfies these requirements. And we understood this actually when we started working on this domain several years ago. We realized that this doesn't exist, and that is perhaps because most of the software development is done by software engineers who are more concerned about the protocol aspects, right? The faithful reproduction of the protocol in simulation. But of course, you know that this protocol is interesting because these are actual experiments and these are actual use cases, right? So for these use cases to be successful, we need to understand that any experiment, no experiment will be perfect, because it will come with various components which will come with their own limitations, whether it is physical process-based limitation or whether it is device-based limitation. So this will happen, and so these limitations also need to be included in your simulation, right? Only then you would be able to predict a reasonable key rate and quantum bit error rate and any other property that you want to predict, which will have a possibility of matching with the experimental results once it is done. So that is why we wanted to come up with something like this. It's a kind of a gap which existed in literature, which we tried to fill with our simulation toolkit, which is called QKD Sim. Okay. So as QKD is becoming commercially viable, advanced engineering techniques are being proposed. Now, direct testing of these techniques in an optical setup is not very cost effective because, who will, we are all poor researchers here, right? So who will give us the kind of resource required to just set up something and see if it is good or not, and then buy again a whole new set of things to make it better? That is not very cost effective, neither is it very judicious use of resources. So QKD Sim helps in quick accommodation and testing of these techniques by enabling simulation of QKD protocols considering physical process models, realistic imperfection, and experimental non-idealities. Okay, and we have tested its prototype's performance with an in-lab implementation of the B92 protocol. So now, what we are doing here in QKD Sim is following what is called the AGIFAL model of software development, where the structure is a waterfall structure. It's a top-down approach, but with agility thrown in various modules so that we can change a particular module without changing the whole simulation. Okay, so it's a modular software that we are aiming to build, whereby the different modules can be replaced with more efficient modules as further research happens in our QKD Sim explorations. Okay. And so, there's just a little bit of detail about the various modules which go in. As I mentioned, it's the AGIFAL model of software development. Okay. This part I'll skip, the bootstrap method for measurement rate estimation. Again, one of those things which we have done to ensure that we are perfectly aware of the exact statistics that we require in order to have a secure protocol. Okay. And you can find details in this paper here, right? And then different optimization techniques that we have done, again, to ensure that our quantum bit error rate is indeed restricted to our Q-bar of 4.8%. Different strategies, we call them A and B, where in one we actually keep the key symmetry fixed and then see what happens to the rest of the numbers, and then in one we don't fix the key symmetry and then see what happens. And the pros and cons of this in terms of security are also explained in our a paper. Okay. But what is heartening is the very nice match between simulation and experiment. As you can see, both of them predict around 50 kilobits per second for the key rate, and the Q-bar is of course restricted to 4.8%. And with the new research that we are now doing, this match is becoming even closer. I just see a question come up on my screen sometimes. One of them I just noted, what is key symmetry? I'll just answer that. So key symmetry means the number of zeros and ones in your key. As you know, a key consists of zeros and ones, right? These are the 2 bits. So then, if the key is not symmetric, I mean, if it's a little bit of asymmetry is okay, but if it's not if it's too asymmetric, what happens is, let's say you have 70 zeros for every 30 ones or something, then this becomes a security loophole, because if Eve gets to know that you have a key asymmetry, then she can use this to perform some kind of an attack on your communication. Okay, so that is why the symmetry kind of is ensured, so that Eve does not have any unnecessary information for her perusal. Okay. So various algorithms that we have developed. This is a snapshot. Okay. Now I go on to the aspect of long distance quantum communications, which is in fact the last topic that I wanted to discuss. All this that we have been doing for the last several years towards various approaches to quantum key distribution, new protocols with higher security, our new simulation toolkit, and so on. It has actually been aimed towards, one of the aims has been towards increasing the distance in quantum communications, okay? And why do we have distance limits for quantum channels? Now, okay, so if I want to do ground-based quantum communication, then typically, 100 kilometers is possible using line of sight based approaches. Up to a maximum of 300 kilometers has been shown, but it's still very difficult. So beyond that, what happens is line of sight is a problem. So if Alice and Bob don't really see each other, or the sender and the receiver in that case, then free space communication cannot be done in that spirit, right? So this is a problem. So in fact, for beyond a certain distance, the Earth's horizon becomes a problem. Okay. Now you might want to say, okay, let us do fiber-based QKD. That's fine. But even if you do fiber, you know that fibers have losses, right? So 0.15 dB per kilometer at best is the loss. So beyond a certain point, you will have to bring in some kind of amplification so that you can do this for a longer distance. But traditional optical amplifiers are not possible in QKD because of no cloning theorem. So you cannot clone or copy an unknown quantum state just like that. In classical, yes, we can. We can just copy it, boost the signal, and then proceed. But you cannot do this in quantum, right? So you need out-of-the-box thinking in order to increase the distance of quantum communication. So there are 2 approaches, let's say 3. One of them is the trusted repeater-based approach. And in fact, this needs to be revised because the Beijing-Shanghai link has happened in China, which is a few thousand kilometers. Then you have quantum repeaters, which actually use entanglement. And we are also working on this particular approach. And then you have satellite-based QKD, which is another unconventional approach, but then of course, something which forms the basis for one of our very important projects in the lab, okay? So towards, the second part, which is about relays, memories, and repeaters, this is a project we are working on under the DST's Quantum Enabled Science and Technology program. And to put it very simply, it reminds you of a relay race, okay? You might remember, you were kids much more recently than I was, so you may remember playing this as well. So there are these 2 groups of people who are, racing. And so one person from one group is carrying this baton and running over to the next one, and then handing it over to one person in the, opposite side. This guy then comes and hands it over to the girl here, and so on and so forth. So this is what, we transfer the baton from one to the other, one to the other. This is called the relay, the very popular relay race scenario. And this is what we want to do with entanglement. We want to actually have, so for instance, 1 and 2 here are entangled, 3 and 4 are entangled. By actually making 2 and 3 meet and performing what is called a Bell state measurement, which I won't discuss in detail, 1 and 4 can become entangled. So I'm actually swapping the entanglement, and this is called entanglement swapping, and increasing the distance over which entanglement can be distributed. And this way I can increase the distance of quantum key distribution, okay? And quantum repeaters, what are they? These are quantum relays with quantum memory also thrown in, because beyond a point you just can't keep on swapping. You need to store information, and so quantum memory also becomes important. What about satellites for long distance QKD? Now, satellite bridges the large gap between ground-based quantum networks. So what is happening here? You have a satellite, it is on ground station A, it is exchanging some sort of a key, then it is in its pass, it is passing over ground station B, it is again exchanging a key, and then there are some operations happening by virtue of which we can use one of these keys to make the other one secure. And by doing that, we are actually establishing a key between the two ground stations, which originally were not connected using any quantum link. Okay, so satellite is acting as a trusted node or a trusted courier, and thus, basically breaking all distance barriers so far in quantum communication. Okay, this is the general idea. You can have the photon source in the satellite and have two photons between two ground stations, or you can have them in the ground stations and send them up. The satellite does the measurement. Okay, and there are different distances that you can reach using satellites and repeaters and relays and so on. And so, of course, long term, the idea would be to combine these various technologies towards even longer distances. Okay, and this is the idea of what is called the global quantum communication network, where you have this essentially this is what we are doing, right? The satellite-based QKD. So these two ground stations are now connected through a quantum link. The keys that this ground station has, they can be then distributed to different service providers through maybe a fiber network even. So you can combine fiber and free space, and together this would form, it can be a network within the country and then between countries, okay, which is the global aspect. And different countries have different approaches towards this. There has been only one successful satellite-based QKD implementation so far in 2 or 3 years back. Okay, these are the various approaches from various countries, and so this is our project, and this is a collaboration between RRI and ISRO, and this started in 2017. It's called Quantum Experiments with Satellite Technology, or the QUEST project. Okay, and so this is the general idea. So as you can see, here I have a ground station, and I have established a key here, and then the satellite has moved, and then it is establishing it between the second ground station. Okay, and by doing this, I'm going to be able to link these two. And as you can see, we are showing geographically distant locations here. So the aim is to establish information theoretically secure quantum communication over large distances, essentially perform quantum key distribution between two ground stations. And as a part of this, we also aim to have a quantum link between India and Canada, which would be, some 13,000 kilometer link, which would be very nice because that would be a new distance record if it succeeds. Okay. These are our portable ground stations at RRI. As you can see, this is one and this is the other. And this is with the dome and the telescope, because of course we're doing free space quantum communication. And this is the experiment that we did in the beginning of this year, where we have been able to establish secure communication between two labs which are separated by 50-meter distance across the RRI campus. Okay, so this is all within the RRI campus. This is one lab, this is the other lab, and this is what we have done. And so here we have demonstrated entanglement-based QKD. And of course, it is a free space quantum communication. And again, this is India's first demonstration of free space quantum communication using an atmospheric channel. Okay. And so these were our preliminary results. And of course, after this couple of months, we have not had any progress because we were in lockdown. Karnataka was in lockdown. We have now again come out of lockdown. And so over the last 3 or 4 weeks, again, a lot of progress is happening in our various projects, including this one. But then here you can see these were the results that we obtained in early February for the key rate and the the raw rate and the error corrected rate, and with this sort of a cuba. Okay, and this was the free space one. Sorry, this was, of course, so the one that I showed here is the in-lab one, which was last year, and this is the free space one, which is the February one. And we have reasonable key rates and cuba, but at the moment we are working on improving these numbers, making them larger and smaller respectively. Okay. And again, this particular work being the first of its kind from our country, we are very lucky that we gained a lot of public interest again in this particular demonstration. And we are very honored with this, and we hope that we continue making significant progress on this and other projects in the future. These are various people who are working on this. And of course, in the current situation, this is how we have been for the last 1 year with masks and safety. And this is, of course, breaking a bit of the social distancing norm, but then, of course, for the sake of the picture. We continue, and we were actually this particular, our works in the domain of quantum key distribution, the first experiment that we did, the physical review applied one, that was recognized as one of the 20 major success stories of the Department of Science and Technology in 2020, as well as our quantum state estimation work, which was the quantum state interferography. Both of them were recognized by DST. And in fact, you might know that we have an organization called the Vigyan Prasar, which again is also has a collaboration with DST. So they have what is called the India Science, which is the nation's science channel. Very interesting channel where they, give us details about science that is happening in our country. And so they also recognized this work as one of the top 10 inventions of 2020. Okay. Right, and so we were very happy with that because, of course, 2020 was not particularly pleasant otherwise, as for all of us, really. So the fact that we were able to get some important and interesting science done is, of course, testament to, the dedication that the team has and, and of course, our funding agency. And so we're very happy with that, and we hope that we continue making these efforts and making new advances as we go along. Okay. So regarding quantum communications, as we just discussed, of course, we discussed the quantum experiments using satellite technology project, which is India's first project on satellite-based QKD. But we are also working on other aspects of QKD. This is integrated photonics-based QKD, which is with the aim of having QKD on a chip. This is in collaboration with Italy under the bilateral program of DST. And, this is something very interesting because if this works and hopefully in near future, this is something which we can envisage using as individuals as well, like people like you and me can perhaps see such usage. It's more like a QKD for the common man project. Then we are also working on quantum teleportation. This is the one that I talked about, the quantum relay and repeater technologies under the DST umbrella program. And we have a project under the Center for Excellence in Quantum Technologies of the Ministry of Electronics and Information Technology. And I believe Samir is also funded by MIT. And so this particular project is a tri-institutional center of excellence in Bangalore. And we are heading the RRI part of this project. And we are working on novel approaches to quantum teleportation as well as random number generation as a part of this project. Okay. I wanted to spend the next 2 minutes, if I may, on Dr. Bhatnagar. Can I speak for a couple minutes more?
Yeah, definitely, please.
Okay, yeah. So I just wanted to spend the next 2 minutes on because students are here in this audience. So it's very important that we realize, there is a lot of interest right now in quantum science and technologies. And of course, we are very happy with that. But then we have to be very careful that, the kind of work that we do. And of course, it also is something that we are doing from representing our country. So it has to be something which is definitely following the standards that need to be maintained in terms of various quantum technologies. And so there is, in fact, a focus group on quantum information technologies for networks, which was formulated by the United Nations. And I'm the invited member in this group from India. And so we are working on, different approaches to standardization of quantum technologies, because of course we need to ensure that if I say that I have developed this protocol and this is what I get, this is something which needs to meet a certain standard. It's like an ISI mark for quantum. And that's very important because otherwise, we won't be able to distinguish between proof of principle, between, demonstrations which are not secure versus those which have taken many things into account. Okay. And so this is something that I am very deeply involved in. And in fact, one of the conferences that I was invited to as a part of this focus group, where they gave a nice overview of the various types of research that is going on in quantum communication. Just wanted to share a little bit of that with the students here. So this is on satellite-based QKD, and this is, of course, the effort from China, where you can see that, they have been able to establish different sorts of demonstrations using the Mischief satellite. This is the quantum network test beds in Russia. Okay, different groups working on different aspects, right? And you can see that there are lots of industries which have shown a lot of interest in QKD systems. So these are, the various sorts of numbers that various technologies have achieved from the Russian perspective. This is their satellite QKD roadmap. Okay. This is the backbone project that I talked about. This is this Beijing-Shanghai link, which is 2,000 kilometers. Okay. And you can see this is the market for QKD systems by end users. And so you can see this is where we are right now, but you can see this is not a linear growth. This is very, very quickly. We expect a lot of the, market to be devoted to QKD systems. Okay. And just to zone in, you can see that we will have users from different sectors, whether it is, civil, government, mobile payment systems, military, of course, and this was done by an independent group. So essentially, this research was done by an independent group which only concentrated on the market value for QKD systems. Okay. Anyway, so with that, I would like to end my talk. And this is, I like to show this particular picture because this is from the last physical conference that we had organized at RRI in January 2020. On quantum frontiers and fundamentals. We have a conference series here. This was the second one, and it was a very nice conference. And so we hope that we can get back to more physical conferences, workshops, and interactions, hopefully in the near future. And this is, members from the lab with some visitors and so on. And so this is a snapshot of various visitors who have come and, good and have shared their enthusiasm as well as knowledge. And it has been a very good journey for the last 10 years for our lab at RRI. So with that, I would like to stop for now and take questions. Dr. Bhatnagar?
Yeah, I think Sonatan is
okay.
looking after that.
Okay. Yeah. So should I stop sharing the screen or because I don't really see much else or should I retain it is the question. How are the questions? Are they based on slides or not?
Ma'am, there are certain questions. Here is Nikhil Gupta.
Okay.
First of all, thank you for such a detailed but simplistic presentation and also giving us an overview regarding quantum communication from photonic perspective. I think that the presentation must have helped the novices as well as advanced researchers to take up their future activities. And they should be proud of looking towards the activities that you have taken up.
Thank you very much, Nikhil. Yes.
Thank you, ma'am. Now, with your permission, the questions that we have received, I just put them in front of you.
So should I stop sharing the screen? I don't see much in front of me except
it is up to you, ma'am. It is up to you.
Maybe I do that, right? Because this is I can always reshare, right?
Yes, ma'am. You can. No problem.
So I have to go automatic and then just stop sharing. Okay. Yeah.
So you can also read the questions from the chat box.
Where exactly? Chat box. Okay. Yes, I can do that.
I just read them. I just read them for the convenience of other audience.
Sure.
So one member from the audience, Subrat Sahu, he has asked that in the Alice Bob experiment, when they discard some of the mismatched codes, is there any loss of information?
Oh, no, of course not. So, thanks for that question. Yeah, it's a good question. But then Alice Bob experiment is a nice way of saying it. So this is, of course, quantum key distribution between Alice and Bob. And Alice and Bob have been traditionally there for some reason. So when we discard the mismatched codes, we actually discard not codes really, it's more like the mismatched basis, right? So we discard those key bits which have appeared because, Alice and Bob have chosen basis because it's a random choice. So they have randomly chosen bases which do not match, because if they do not match, the idea is there is no sending of these bits, right? So Alice is left with a set of bits, Bob is left with a set of bits, and they need to be the same. And so in order to do that, you have to discard those which correspond to bases which do not match. And secondly, it can also result from an eavesdropping strategy, right? So if there is an eavesdropper who's trying to do something to gain information about this key distribution, so then this eavesdropper might intercept this photon, let's say, on its way, and then do some measurement, right? And so if they do some measurement and then send another photon to Bob, this is called man in the middle attack, by the way. And so then what will happen is that inadvertently the bit value, there is a probability that this bit value will change, right? So then you don't want to keep bit values which correspond to mismatched bases, because already even after that you will be left with a few which will be different because of errors. So you want to get rid of the mismatched bases, because that wasn't the intention that Alice and Bob had. They wanted to choose the same basis, but they cannot do that because it's random. So there will always be the probability that there will be a mismatch. So there is no information, no useful information lost. Of course, when you discard something, there is some information that is lost, but this information is not useful for the current implementation. Yeah.
Okay, I think this must have answered his question. So there is another question from Anuj Agarwal. Yeah. Do we not have any way of repetition for long distance communication using prepare and measure scheme based QKD protocols?
Yeah, that's of course a very good question. So indeed we do. And in fact, this Beijing-Shanghai link that I talked about, this backbone project, that is about, so as I said, there are three ways. So the first way is the one that actually could involve, it is not in, dependent on a particular scheme for QKD. It could be prepare and measure as well, where what you do is, you basically keep replacing Bob. So let's say Alice and Bob are sharing, are establishing a key, and they're separated by 100 kilometers, let's say. Then after that, let's say that Alice is sharing this with Bob 1, okay? Then what happens is we establish another link between Bob 1 and Bob 2. So Bob 1 now becomes the new Alice, okay? So this way we can keep having multiple Bobs. So Alice to Bob 1, Bob 1 to Bob 2, Bob 2 to Bob 3, and so on. And so these are what are called the trusted, repeater-based nodes. So these are trusted nodes, okay? So these trusted nodes lead to this sort of a long network structure. So here there is no entanglement involved, but the problem is this trusted thing. So we have to trust these nodes. So for proof of principle, it is good, but if we really are worried that one of these nodes could be sabotaged, let's say, by some malicious party, then of course the whole thing goes down, right? So there is a way of doing this, as I mentioned, this repetition by using trusted nodes, but then this trust is important there. I hope that answers that question.
Anuj again asked another question. After key establishment via satellite, the encrypted classical information exchange means how the communication will take place. Is it over the fiber or through free space?
Right. Yeah. So then see the key. So you have established a key between the two ground stations using the satellite. But then after that, one is free to use this key to have the, so as you can appreciate, the communication aspect comes after the key distribution. So you can use this key to then encrypt any message and then send it to your intended receiver. And that channel could be anything, really. So there is no restriction on that particular channel through which you are doing this, because of course you are using a key which has been established using quantum mechanics. So that key is now ready to be used for secure communication. So your communication, the next step, there is no restriction to using, you could do it through any means, yeah, fiber or free space.
So there is a question from Mrinal Kanti Sarkar. I think you have already answered it, but I will ask it again. Let's say Bob is sending one image to Alice. They are apart from each other by certain distance. Can some other third party distort the encoded image in the way between Bob and Alice, or is it completely impossible?
Yeah, so this is the point. So you see, actually, you're right. I did answer towards this question, but just to repeat, so what Alice and Bob are doing are establishing a secure key between them. Then after that, Bob can use this key to send an image to Alice. And so if, so the idea is that this key, is now tamper-proof. So then, of course, the image will also go to Alice without any such, intervention, because the key is already secure. So the key distribution is the part which we need to secure, because if somebody gets hold of the key, then that person can use that key to decrypt the information and not the intended receiver. Okay, so the one has to distinguish between the key distribution and then the subsequent use that it is put to, let's say. And so image transfer is one example. Of course, when you say, is it completely impossible? I mean, nobody will say anything is completely impossible. So what we say is quantum key distribution is information theoretically secure, but we never say unconditionally secure. At least the people who work in the field never say unconditionally. Because you see, through information security, information theory, we know that it is as secure as it can get. Okay.
That is another question.
Please.
There is a question. I think it is a kind of a detailed one, but the audience has asked it, that Snehal Sharma. I think she has asked about brief details on tools and algorithms that you have used in QKD.
First of all, something cannot be brief and detailed at the same time. Okay. So, tools and algorithms. Well, I will interpret the question my way, because it is up to my interpretation. So, yes, regarding tools, of course, it has been established using optical methods, right? Like please have a look at the publication, because indeed it is a very long one, and I'm sure it will answer many such things. So, there are different optics and optomechanics that is used for establishing QKD, as well as electronics, right? So if I were to answer tools, it would be optics, optomechanics, and electronics, as well as FPGA. Yeah. And then, of course, in terms of algorithm, as I mentioned, we have developed our own, and that is called QKD SIM. So we did not use any publicly available ones, for the reasons I hope you appreciated, that they don't really solve our purpose of giving us an answer which meets our expectations once the experiment is done. So we've come up with our own simulation software, and you can find some details in the publication. And as I mentioned, that we are in the process of patenting this as well. And once that is done, then it will be available in the public domain for usage. Yeah.
Ma'am, there is another question. I think it is the last one. In BB84, if we discard the bits whose keys doesn't match for Alice and Bob, doesn't the information in those bits lost? I think it is the same question like the previous one.
It's the same question as the previous one, yes. So as I mentioned, those bits don't carry any useful information that I would regret losing, right? So, the idea is that Alice and Bob need to remain with the same key bits on both ends, without, of course, sending it to each other, because then it defeats the purpose. So they should remain with the same set of bits on both ends, so that they can then use it for the communication aspect. Yeah.
Ma'am, this is the end of the question and answer session. Okay. Thank you for your patience. And now I invite Mr. Hitesh Mehta for the formal vote of thanks. Mr. Hitesh Mehta. Hello. Am I audible, Mr. Hitesh?
Yes.
Okay. Please carry it forward, sir.
Yeah. So thank you, Dr. Urbasi, for this wonderful talk. It was very interesting, and we had very good attendance. I think the students and other research scholars enjoyed it well. And we hope that you will come again for some other occasion. We are our Photonics chapter is very young. We recently formed it, but we are planning many exciting these workshops and conferences. And we would like you to be associated with our chapter in some way and share your knowledge in the future as well. Thank you
Sure.
again for sharing your time, and see you again. Thank you.
Thank you very much. And of course, that is when Dr. Bhatnagar actually discussed this with me, I took it up immediately because, it's always very nice to talk to the younger people because, they retain an enthusiasm which sometimes we tend to lose as we grow older. So I always like to retain mine by, keeping the surroundings younger. And so this is always always a good opportunity to try and explain some of what we do to the younger minds, and I'm sure some of them will hopefully take this up later on and make great contributions. Yeah. So thank you very much to the IEEE chapter, as well as, of course, and Dr. Bhatnagar for making this happen.